In this video, we're going to look at how to write the equations of trig functions when given the graphs. And I have graphs that all 6 trig functions could be used. And the way you start is you look at the graph, and I'll start with the one on the left-hand side there. And you want to identify the kind of functions that could be used. And so if I'm looking here at the one on the left-hand side of the screen, this has to be either a sine or a cosine wave, just because of the key features. And so once I identify that, now I'm starting to look and say, okay, well, the general form of a sine or a cosine wave is y equals a times sine or cosine, one or the other, of w times x minus h plus k. All right, so kind of in that form, and depending on where you go, if you looked on the internet, looked in a textbook, they could have some different letters. But these are the ones that I've used in class, and it's on our notes, so I'm going to stay consistent with that. Now, A is the amplitude, and K is the midline, so I'm going to identify those two first. So K is my midline, and looking at the graph, the midline is going to be halfway between vertically the maximum and the minimums, so that's going to be right here. So my midline is at -2, so that's what K is going to be. The amplitude is the maximum displacement in any one direction from the midline to a peak. So my amplitude would be 2. I got an amplitude of 2, and I have a midline of -2. Now, from here, we want to find our period. Number of ways to find period from a graph. I can look and say, all right, well, for sine and cosine, one way to find period is to go from 3 consecutive midlines. And the overall span between those is 1 full period. I could also do from max to max or min to min or a couple of other combinations as well. But doing it this way, 3 consecutive midlines, we get a period of pi radians. And now we need to solve, I have the constant W, which is our horizontal stretch or shrink factor. And so what we do is, remember, period is equal to 2 pi divided by our horizontal stretch and shrink, which I have 2 pi over W. So I'm going to set that equal to pi, and then I'm going to solve for W. When I do that, I multiply W to the other side, divide by pi, I get W to equal 2. So I have W, A, and K. Now that I have those 3, now I'm ready to start trying to write the equation. And what I have done is I have picked a couple of reference x values to help us do this. And so the first one we have is using the reference x value of x equals 0. And so what I do is I go to x equals 0, I look on the curve, and I classify the kind of critical number that is. Well, that's a midline. And so since I'm basing my function off the reference x value that's a midline, we want to use sine because sine starts at its midline. So I'm going to start writing this equation here. So I have y equals, and we're going to use the sine function, so it would be 2 times sine of W, 2, times x minus the reference x, which is 0, plus our midline on the end, which is -2. Now, I have to now look at this graph and make sure that my equation is written correctly. For sine, if you start at your midline and then proceed to go below your midline to a minimum, the sine wave has to be reflected, so I have to add a negative sign out front. So here's our equation based on that reference x value. Y equals -2 sine of 2x minus 2. Now I want to look at trying to write the equation for the same graph, but basing it upon a different reference x value. So let me switch colors here. And we're looking at the reference x value of 3 pi over 4. And so I go to my graph and I see what kind of critical point is that at 3 pi over 4, and it's a maximum. Well, anytime I'm basing my equation off a peak, I'm going to use cosine. And if it's a maximum, cosine is positive. If it's a minimum, cosine will be negative. So I'm ready to start writing here. I can say y equals amplitude 2, it's going to stay positive because we're at a max, cosine of w times x minus, now h is this reference x value, so x minus 3 pi over 4, close up my parentheses, and midline on the end. And I don't have to distribute that 2 and rewrite. What I have right there is sufficient. All right, so let's write the equation of a sine or a cosine wave from its graph. Now let's look at a different kind. Let's look at a secant or cosecant graph. Now, the key characteristics for secant or cosecant graphs is that you'll see the stereotypical u's and n's. So anytime I'm trying to write the equation, I want to identify the possible functions. Well, we could be secant or we could be cosecant. And the general form of a secant or a cosecant wave is very similar to that of sine or cosine. I can say y equals a times secant or cosecant of w times x minus h plus k. Now, technically secant and cosecant, they don't have amplitudes. But remember, they are really the reciprocals of sine and cosine. So if I wanted to look at this and say, all right, well, to determine the amplitude, I'd start by trying to figure out what the midline is for the sine or the cosine wave. I would look, and you find the peaks. So a maximum and a minimum, or excuse me, a max and a min. And then I want to find the spaces halfway in between there. What y value is halfway in between positive 1 and negative 3? That would be negative 1. Right here. That is going to be k. So I know k is negative 1. Now I would find my a, which would be the amplitude if it was sine or cosine, but that's going to be how far away from that midline that we just drew is it to get to one of those relative extremas. So, and it winds up, it winds up being 2 units to get from that midline to one of those relative extrema. So I'm going to say a equals 2. Now, we want to find period. Well, period, just like for sine and cosine, a period is how long it takes the graph to complete one full cycle. So I'm going to find 2 identical points on a graph. About 2 of these relative maximums here. And the distance along the horizontal between those 2 is my period. So my period from the graph is going to be 5 pi over 16 minus negative 3 pi over 16, or that makes 8 pi over 16, or pi over 2. Now, I will need to figure out what the stretch or shrink factor is that made the period become pi over 2 instead of 2 pi. So I'm going to remember 2 pi over w is equal to the period. And I'm going to solve for w. So with that, we're going to say w equals 4. So now I have a, w, and k. And we're ready to start writing. So to write our equation, we would need to use some kind of reference x value, and I don't have these pre-written. So I'm going to pre-write my reference x values now so we can write an equation. So let's use the reference x of, let's go negative 3 pi over 16. All right, so I'm looking at, and I go to negative 3 pi over 16 and say, all right, well, what is happening here on my secant or cosecant curve? Well, we need to figure out, even before that, is, well, if I base my equation off a peak, do I use secant or cosecant? Well, remember, it's the same answer to the question as which function, sine or cosine, do I model based off of max or min? I model using cosine when modeling off a maximum or a minimum. So therefore, if I pick a peak, I am going to be using the reciprocal of cosine, which is secant. So I'm going to be using the secant function if my reference x value is a peak. So I'm going to go ahead and start writing y equals a times secant of w times x minus our reference x value, so that makes x plus 3 pi over 16. And then our midline on the end, so minus 1. Now I just got to figure out, well, is it going to be positive 2 out front or negative 2? So if I look in here at that point that we're using a little closer, and remember, I technically have this cosine wave that's in here. That would be graphing, that I'd be graphing as well on the inside. And this would be a minimum for cosine. Now, if I was writing an equation of a cosine function based off a minimum, I would have to make my cosine equation negative, which means that the secant function would have to be negative as well. Let me choose a different one, a different reference x value. Let's go to and use the reference x value to write an equation of 3 pi over 16. So I want to go to 3 pi over 16, and graphically I'm going to change colors here and say, all right, 3 pi over 16, well, I don't see any part of the graph there. So it's not a peak. But the graph is starting to show unbounded behavior. So 3 pi over 16 is a vertical asymptote. Like, okay, so a vertical asymptote. Now, I'm going to continue on. I'm going to make, I started that graph in orange, but I'm going to continue to make that graph here. Did it? I got to fix that. I got a little off there. All right, so I'm looking, and at 3 pi over 16, it's undefined. Now, if I had this wave of a sine or a cosine wave, and I'm looking and say, well, where would the sine or cosine wave be at that point? That would be at the midline. Now, if I was modeling the dotted curve that I just made there in green, I'd be using sine. But I'm not writing the equation of the dashed line, I'm writing the equation of the red one. So the reciprocal of sine is cosecant. So if I modeled based off of vertical asymptote, I'm going to use cosecant. So I'm going to go ahead and start writing y equals 2 cosecant of w times x minus the reference x value, the x value we're using to construct our equation, so it'd be x minus 3 pi over 16. And then minus 1 on the end. Now I have to choose if it's going to be positive or negative. Well, if I was writing the sine equation, and I start at a midline, I go down to sine's minimum, sine would have to be negative. So if sine has to be negative, cosecant has to be negative as well. So that's how we write the equation of a secant or cosecant function from its graph. Now let's look at a third type. So let's look at this one right here. And I want to identify the kind of function. Well, the only two kinds of functions that look like this are tangent and cotangent. So tangent and cotangent functions. All right. Well, their general form is going to look just like the other ones. So just to keep my letters consistent. So a times tangent or cotangent, w times x minus h plus k on the end. Well, this can be a little tricky because it's hard. It can be hard to figure out where the point of inflections are, especially if you don't have a good viewing window. You're looking to find k. K is the point of inflections. A point of inflection is where the curvature of the line changes, where I go from being curved down to curve up. And the one that I see is right here at pi over 8 because we're going from being curved down to curved upward, which means that by definition is a point of inflection. So I'm using that value of -2 as my k. So I know what k is. Now, I can't necessarily go find out what a is right off the bat. I have to kind of save a for a minute to come back to it. And after I find my period, so I'm going to jump in to find period here. Well, if I had two of these point of inflections, my period would be the distance in between the 2 points of inflections, but I don't. I only see one. So instead, what I'm going to do is I'm going to look for vertical asymptotes because for tangent and cotangent, the distance between the two vertical asymptotes is also equal to the period. So I'm finding two vertical asymptotes. There's one of the y-axis, and there's one at pi over 4. And the distance in between them is my period. So my period here is pi over 4 radians. Well, we can go ahead and solve for w because the normal period of tangent or cotangent is pi. So to find the stretch of the shrink factor, I'm going to say pi over w equals pi over 4, which means that w for our equation has to be 4. So I have w and we have k at the moment. Now to try to figure out what a is, our vertical stretch. There is no amplitude for tangent or cotangent, so I just keep my letters the same as for the other trig functions, but a is our vertical stretch. Now, to find the vertical stretch, you want to look for the change from the point of inflection when you go a quarter of the period, which would be, actually, if I'm here at my point of inflection, how far do I change vertically when I get halfway between it and the vertical asymptote, which is here? Well, halfway between pi over 8 and pi over 4 is 3 pi over 16. So I'm looking and finding the functions. Where's the function at 3 pi over 16? And I'm looking for the change in its height. The change in its height is 1, 2, 3 units. So that means A is 3. That's my vertical stretch factor, because it would be 1, but I made it 3. So that's going to be my vertical stretch. So we have A, we have W, we have K. And we're ready to start writing the equation. So I need some reference X, and I didn't provide these before I started, so I'm going to write them here. I'm going to say, let's say we have a reference X value to write an equation off of pi over 8. Let's start with that one. Well, to pick what function I use, I need to know, well, which function, tangent or cotangent, starts at its point of inflection. Well, to answer that, just ask yourself, well, what's tangent of 0? Tangent of 0 is 0. All right, so tangent of 0 is defined. Cotangent of 0 is undefined. So cotangent would not be the function of choice that I would use to model my function off of a point of inflection. In fact, cotangent has to be based on a vertical asymptote. So for pi over 8, we have to use tangent. So I start writing and say y equals a times tangent of w times x minus the reference x value that we used to build our equation, and then k on the end. And then the last question we have to ask ourselves is, well, is it positive or is it negative? Tangent is an increasing function unless I reflect it. So this graph currently is increasing within the bounds of the vertical asymptote, so I leave it positive. Now, let me choose a different reference x value. So a reference x value of x equals 0. So if I wanted to create a cotangent equation for this same graph, I would have to base my function off a vertical asymptote. Cotangent, we write equations off vertical asymptote. So I got this vertical asymptote at 0. Cotangent of 0 is undefined, so that's why I pick my vertical asymptote. So I'd say 3 times cotangent of 4 times x minus 0, so I'm just going to write 4x, minus 2. Well, cotangent is supposed to be a decreasing function on its domain. This graph is increasing. So that means what I have to do to my cotangent function is I have to make it negative. So that way it would flip the graph of cotangent and make it become increasing. And there are 2 equations